Hello, my name is Lindy Humphrey, and this is my lab report for Physics 2211 Oscillations. To introduce this lab, the purpose is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We are going to use Tracker in this lab, which will observe the motions and glow script to create a computational model to predict the object's motion and energy exchange. And then to give a brief overview of the results of this lab, we will see that the total change of the system remains constant at 0, demonstrating the energy principle. We also need to make sure we identify a few important physics principles, including Newton's second law, which is a system's change in momentum proportional to net force, applied, represented by F net equals delta P over delta T, and the energy principle, which is a system's change in energy equals the sum of work done by the surroundings and thermal energy, represented by delta E surroundings equals W surroundings plus Q. And then because we are isolating the system, we do not have actual surroundings we have to account for in this lab, but our system includes the mass, the spring, and the earth. Using the video we were given and putting it in Tracker, we can determine that the mass of the object was 0.402 kilograms, and the initial position was negative 0.017, negative 0.632, and 0 meters. L, or the stretched length of the string, was about 0.7 meters, and the initial velocity was this zero vector, meters per second. We now have to solve for a few things to find the initial conditions. To solve for t, which is the oscillation period represented by the formula 2 pi times the square root of m over k, we have to find the average time for each oscillation period. I took the first 3 intervals and found the average to be 1.5197 seconds. We then have to solve for k using the formula identified on the first part, and rearrange it to be k equals 4 pi squared times m over t squared. Plugging everything in, we get k to equal 6.872 newtons per meter. Lastly, we must solve for the relaxed length of the spring, which is the equation F net equals negative k times L minus L naught times L hat plus mgy hat equals 0. We can then arrange it and solve for L naught, which is 0.1261 meters. We can then use this to fill in our glow script code with our initial conditions and everything we have solved for in the previous slides to run the code and see the movement as seen here in the glow script code. Here are the results given to us through the glow script code. We are given 2 graphs that show the oscillating functions of what is going on between the observation and computational models. As time goes on, the 2 graphs start to deviate more and more when it had originally started going pretty close together. And that could have been caused by a couple of errors, including that the system is not actually closed, meaning other forces or factors could have influenced our system during this lab, changing its movement from what would have been predicted, as well as the tracker analysis could have been off, as the center of mass we would establish in Tracker may have been off from the actual position. Lastly, we must answer our what does it mean questions. The first question asks, is the energy principle satisfied? And the answer is yes, it is. The change in energy must be 0 to satisfy this principle, and since no external factors are influencing the system, that is correct. This shows that the total change in energy is 0 or remains constant as 0 as everything balances out, as shown in this graph here. Next, we have to compare our 2 oscillation periods. To do so, we did the exact same calculations as before, looking first at the x graph and then looking at the data from the y graph. We took the average for each of the periods first to find t, and then plug them into each of our k formula. Plug each of them into the k formula, and as we can see, they are a bit different from each other when we solved it. So we know that depending on the direction that we choose, it causes deviations which can affect the spring constants in the graphs. And that is all. Thank you for watching.